One major problem associated with scale tank testing is that of reflections. This model is reflecting waves back towards the wavemakers. Although the effect is not obvious to the eye in a mixed C spectrum, we can see it clearly if we watch again as the waves first strike the model. When a model under test sends reflections back at the wavemakers, there's a real danger of waves building up which simply bounce back and forth between the two. This would quickly degrade an experimental C spectrum. To demonstrate how an absorbing wavemaker deals with this problem, we'll look at a worst case. The wooden board at the left end of the tank is an almost perfect reflector. Acting on a command signal from the oscillator, the paddle sends out a packet of 7 waves, then stops. The waves are reflected back, but now, and with a 0 command signal, the paddle moves so as to absorb the unwanted waves. Calm water is quickly re-established. Repeating the demonstration, the oscilloscope compares the command signal, shown on the top trace, with the actual movement of the paddle recorded below. When the command signal drops to 0, the wavemaker still actively responds to it and keeps moving to produce 0 waves. It's effectively removing the unwanted waves from the tank. The absorbing action of the wavemaker is an example of viscous damping achieved using force and velocity feedback. A tacho generator coupled to the shaft of each drive motor produces a signal which is directly proportional to the wavemaker's velocity. A second device measures the force exerted between the paddle and the water. Because the transducer is built into the paddle in this way, its signal is an accurate measure of the total force on the wavemaker. The force and velocity signals are processed and fed back to produce a modified command signal. This is then amplified and sent out to drive the wavemaker motor. The key feature of the system is this. It allows the wavemaker to absorb reflections at the same time as it generates new waves. In this extreme example, the wavemaker is sending out a continuous wave train while simultaneously absorbing its reflection. The result is a near-perfect standing wave. The float wave gauges are positioned at a node on the left and an antinode on the right. A signal from the right-hand gauge demonstrates the quality of the wave train. Compressing the timescale allows us to observe the stability of the long-term envelope. Without absorption, this standing wave would be impossible to make.